All right, welcome back. This is a continuation lesson as it pertains to electromagnetic induction because what we're going to see now, because we have been looking at different ways how electromagnetic induction can be used in various applications, such as the how the generator works, right? The whole aspect of electromagnetic induction is used in that industry. Now, when it comes down to a thing like transformer, this, as the name suggests, transformer, it has transformed the way how things work in a lot of devices, right? And we're going to look at how it works. How is it that we can take that knowledge of electromagnetic induction to essentially use this simple application to do something in in the world of electronics, and also just make life easier in some regard. By the way, now this is what a typical transformer looks like, right? What a transformer will have, it will have wires wrapped around a soft iron core, right? So on one end you'll have wires wrapped around this side, on another end you would have wires wrapped around this side. As you can see, none of the wires are connected, right? None of them are connected. But I'm going to show you what is happening here, right? This side is what we call the primary um, winding, or you could say that this is the primary side of a transformer. You have the secondary side of the transformer, and I'll explain to you why we call this side the primary and why we call this side the secondary. Be mindful of the symbol so that whenever you see it, this is the symbol here that pretty much depicts what a transformer looks like if you're looking at a schematic diagram. So that's what it looks like. All right, where we just have the curly wires here with two, this is basically the iron core or the metal core inside here, right? The iron core, right? And then you have the secondary end on this side. We're going to look at it and see how beautiful this entire application is. Now, the reason why this side is called the primary side of the transformer is because this is where your alternating current, this is where your alternating current is connected to. So in most cases, a transformer is literally used to do several things. I'm going to talk about it soon. But in the operation of a transformer, it needs an alternating current, right? Alternating current is the same thing as what we call AC, and the schematic for that is simply a circle with a wave inside of it, showing that it's alternating. So that's your power source. And this side will be the positive, this side will be the negative, right? Now, if you know anything about alternating current, right? Alternating current moves back and forth. The flow of the current reverses. So at one point, the current will be flowing in this direction. Then another time, it's going to flow in the opposite direction, as you can see right here. So at first, let's look at it. It's kind of hard to see, but as you can see here, some current is flowing this way, right? Then it stops and allow the current to flow the opposite way, right? So that is just what we're saying. That when it comes on to an alternating current, it allows the current to flow in the positive region, then it stops, then it allows current to flow in the negative region. So that's typically how an alternating current works. And as you know, with an alternating current, this is how the wave looks. It's a sine wave. And of course, this side is the positive side. And then on this side is the negative side. Right? You would have negative voltage on this side, positive voltage on that side. Now, so with how the transformer works is that whenever you take alternating current, as you can imagine, you're basically allowing electrons to flow around the wires here. And if you remember anything about this, if we have wires wrapped around in such a manner, this becomes a solenoid. And if current is flowing through a solenoid, a magnetic field is generated, right? So that's a beautiful thing. So once current is flowing through this thing here, through these wires, you essentially have created a solenoid. And with any solenoid, what it does is that it creates a magnetic field. It's going to create a north and a south pole distinctively. Now, what we're going to see is that this iron core, right? This iron core right here, because of how the material is, or the nature of the material, this iron core, or in a sense, you can call it, yeah, we can call it the iron core or the transformer core. It's going to become magnetized. It's going to become magnetized by nature of the current flowing through the wire. This material inside of the solenoid is going to become magnetized, and with that becoming magnetized, what you will see that the entire iron core has now become magnetized, right? The entire magnetic core, or the transformer core, becomes um, magnetized, which means that it's now a magnet, right? And in that process, what you're going to see happening is that as a magnetic field is passing through a wire, right? If you know anything about that, remember we said no, if the magnetic field is moving through a wire, then what is going to happen is that it's going to allow current to flow. So that's how a voltage or an EMF is induced in the secondary coil, right? That's how the voltage is induced, because you have a magnetic field that is passing through it. Now, one of the things that is going to happen next is that, remember, we're talking about AC current. So at first, let me see if I can use a different color. At first, the current would have been flowing in that direction, right? But as soon as it reaches this point, the current stops and then starts to flow in the opposite direction. If the current is now flowing in the opposite direction, it means that the magnetic field around the solenoid is going to change. So it's no longer going this way, but it's now going the opposite way as what you're seeing here, right? It's now going the opposite way. And with that being said, as you can imagine, the entire iron core is going to become magnetized. And with that now, the magnetic field is going to pass through these wires, right? And as it passes through these wires, it's going to allow the current over this side to also flow in the opposite direction. So, in essence, you will be basically still creating an alternating current at the end of the day, right? You will still be creating an alternating current at the end of the day because of the whole change in the flow of the current. The thing about this, guys, is that it happens very quickly. It happens very quickly, so you will not be able to observe this, but it happens very quickly, right? That's typically how the transformer works. Nothing too hard, nothing too easy at the same time, right? So we're going to look at it in greater depth. Now it says varying current in the transformer primary winding creates a varying magnetic flux in the iron core and a varying magnetic field impinging on the secondary winding. This varying magnetic field at the secondary winding induces a varying EMF or voltage in the secondary winding due to electromagnetic induction, right? So that is just typically describing how it works, right? There might be easier ways of describing it, but this is the real way of talking about what is happening with the transformer. All right. Now it says that the primary and the secondary windings are wrapped around a core of infinitely high magnetic permeability. In bracket, we see here soft iron core, so that all of the magnetic flux passes through both the primary and the secondary winding. It says that the core is laminated to reduce power loss due to eddy current induced in the conducting core by the magnetic field. So in a sense, let's just look back at the um, the um, the transformer. So let's imagine that this is just one side of the transformer. We're not doing everything. I just want to show you something here about how the transformer works per se, right? So this is kind of like what it looks like from a different standpoint. Now I do this because I want you to see something here, right? When a transformer, when the iron core is positioned, imagine that these are the wires here, right, wrapping around, then you have another set of wires wrapping around. Now, one part said that the iron core is laminated, right, to reduce power loss due to eddy current. What we mean by laminated is that it is cut, the iron core is cut into thin slices. So it's cut into thin slices, right? So each of basically inside of the iron core is not just a complete piece of metal, right? It is sliced up in pieces, small pieces. So that now makes it would essentially reduce what we call eddy current, because one of the things you have to understand is that um, one of the things you have to understand, you see, is that the soft iron core is a metal, right? And if if and as you can imagine, wires are wrapped in around a metal. So of course, it means that this soft iron could essentially become a conductor, or it could conduct. But what we do now is to cut it up in small pieces, cut it up into small pieces like that, and that would sort of like, you know, reduce the power loss. And of course, you could have used some type of oil in between the barriers, in between the the pieces that you would have cut up to just kind of reduce power loss at the end of the day. Because as we said, that because it's a conducting material, soft iron, then you would expect that it could conduct a small amount of current, which we would generally call eddy current. Eddy current. All right. Now, one of the beautiful things we just said a while ago, that based on how the the material is, the iron core, we said that it has very high permeability. So what that is telling us is that whatsoever the magnetic flux is on this side, it's the same magnetic flux that will be on the other side, because of the fact that it would not have lost any of its magnetic property in a sense. So all of this, so whatsoever magnetic force or magnetic flux that is on this side, it's the same that would be on the other side, or right throughout the entire thing. So with all of that being said, we can come up with an equation using Faraday's law that speaks to, what is happening on each end of the transformer. So one of the first things, let's see if we can draw a transformer here quickly, right? Let's see if we can draw a transformer right here. And as you can imagine, I have an alternating current, right? Connecting to the wires on this side, right? Positive, negative. And of course, your secondary coil, right? Something looking like that. So this is your um, secondary. This is your primary. And as you can imagine, there are several turns of the wire wrapped around the primary coil. Having said that, we can now consider what we call it now, Faraday's law or Faraday's law of electromagnetic induction that says that the induced EMF E is equal to the number of turns times the rate of change in magnetic flux, which is d of the magnetic flux, right, divided by dt. Good. But as you can imagine, the EMF that is at the primary is basically the voltage that is coming from the primary, or coming from the alternating source. So your voltage at all times is the one that is coming from the alternating source. That would be your voltage, so to speak. And having said that, depending on the number of turns, then that will tell us how much magnetic flux would be generated in the iron core. Okay, so we could just simply rewrite this to say that Vp is equal to Np, because on the primary there will be a set amount of number of turns, right? And then we, obviously times that by the rate of change of magnetic flux. Similarly, on the secondary end, right, you know that an EMF is going to be induced in the secondary coil. Now, on the secondary side, there is n number of turns in terms of the wire, right? And of course, we said that the magnetic flux, the rate of change of magnetic flux will be the same. So we could say that we could start off with this to say that E is equal to Ns, right, times the rate of change of magnetic flux, right, where E is going to be Vs times Ns, right, d of the magnetic flux, change in magnetic flux with regards to the change in time. So if I wanted to find out my voltage on my primary, I could have gone ahead and used all of this information here to basically find out that information, right? But what we're going to do here is to essentially, I would say we could equate the equations in a sense. We could equate them, right? We could equate them, but let's divide them instead. Let's divide them. Let's divide the primary. Well, divide the secondary by the primary just to come up with an equation. So we'll do that right now, right? So if we were to divide these two equations that I just wrote a while ago, right? If we were to divide them, then what you would essentially see, so we're dividing Vs, right, equals to Ns times the rate of change in the magnetic flux. We're dividing that by Vp by Np d of psi by dt. Then we can cancel out something because the rate of change of magnetic flux is the same. So what we're now left with is the universal equation for whenever we're dealing with transformers. And what you're going to essentially see is that this equation is going to help us in finding out certain information for the transformers. So right, so you can see that it's almost like a ratio in a sense, right? And what you'll essentially see that there are some inversely proportional relationship that's going to take place. One of which is to say that if the number of turns on the primary decreases, then chances are the voltage on the secondary would increase, right? And you're going to see that eventually when we, deal with it differently, right? Another equation that will come in very handy is an equation for power, right? As you can imagine, current is flowing through the wires, and there's a voltage that's going to be induced both in the primary and the secondary coil, right? So what we could consider whether power is being lost, which which in real life that happens. But what we're going to do, we're going to assume that there's no power loss, which means that no heat is given off in the transformer, and then we say that the transformer is an ideal transformer. So whenever you see that the transformer is an ideal transformer, it means that the power in power in is equal to power out, right? So what they're just saying is that this transformer is 100% efficient. So we could say that it's 100% efficient. That's what we're literally saying here. Whenever power in is equal to power out, and power in is basically V of P times VI. Let me say that again. VP times IP, because that's the power in. Power in is always into the primary, and VS times IS is power out. So we could have, you know, trans. Well, let's rearrange this. So by rearranging this, we could get that. We could get another equation that we could write to say that, you know, we could write it as such. If we want to bring the i's by themselves and the v's by themselves, then you would see that VP divided by VS is equal to IS divided by VP. So that's typically another equation right here. So there are two equations now. There is this one, right, that links the voltage and the number of turns, right, and also one that links the current. But we could also come up with another one, right? We could also come up with another one where it involves the number of turns with power with current. But you know, I mean, if you know that, you know, VP, right, divided by VS is equal to, if it's equal to IS upon IP, right, we could do a little bit of stuff right here to show you that, you know, all of this is equal to the same thing right here, right? So the most important one is this, and of course this one as well. So if you don't remember this equation, just start out from the fact that power in is equal to power out. This one, you just have to remember it to say that, you know, the voltage on the secondary is dependent on the number of turns on the secondary. The voltage on the primary is dependent on the number of turns on the primary. All right. So let's see now. Now there are different types of transformers, and this is where the fun comes into play, right? We have two specific types of transformer. We have what we call a step up and a step down transformer, and it says that a step up on a transformer does two things. It either lowers or raises the voltage of the alternating source respectively, right? By utilizing electromagnetic induction. So depending on certain things, right, then it's going to vary. It's going to lower or raise the voltage, right? Now it says that when the number of turns on the secondary is greater than the number of turns on the primary, then this type of transformer is going to be a step up transformer. I'll show you a diagram soon. It says that this means that the voltage at the secondary will be greater than the voltage at the primary. So this is kind of like one of the huge advantages of transformers, because what you're literally doing, you're taking a lower voltage, right, and then now you're stepping it up to a higher voltage. That's one of the amazing thing about transformers, and it is used widely in different industries. You know what I mean? Like when you consider like a manufacturing industry that needs really high voltages to power up their devices and so forth, JPS would produce or give them a usual amount of 120 volts, right? But because of transformers now, then it means that you can now step up that voltage to giving you more voltage because of the design of the transformer. So we're saying that for a step up transformer, it's simply when the number of turns on the secondary is greater than the number of turns on the primary. Now, on the other end, the flip side now, when the number of turns on the secondary is less than the number of turns on the primary, then it tells us that there are fewer turns on the secondary, and not only that, it tells us that the voltage on the secondary is going to be far less than the voltage on the primary. And what we call this now is a step down transformer. So it's almost like a step, right? So for your step up transformer, you're increasing voltage on the secondary, right? But as soon as you know come down the step, you're realizing that you're decreasing voltage, which just means that you have less number of turns on the secondary. So we're going to look at the diagram soon. Hopefully I have them here. Maybe I don't have it on this slide, but I'll show you what it looks like in a few. Now, it says that when it comes down to transformers, right, there are some amount of energy loss, right? There are some amount of energy loss in a transformer, and we must know how those energies can be lost. It says that if the transformer were 100% ideal, then it tells us that the input current would be equal to the output, well, the input power rather would be equal to the output power. As we said, that's when you have an ideal transformer or 100% efficient transformer. It says, however, this is not the case, right? Because it says, as change in the magnetic flux in the iron, right, causes the iron atoms to constantly align with the fields, and energy is lost as what we call magnetic heating. So because the atoms, right, in the iron has to be constantly be, aligning themselves with the magnetic field, then that constant moving back and forth, because as you know, in the iron core there is a fluctuation, there's a change in the magnetic flux from time to time. So what you would see now, because of that complete movement there and then, it's going to create magnetic heating, and so amount of heat is going to be lost, or energy is going to be lost as what we call magnetic heating. It is when an alternating current passes through the primary winding of a transformer, it says that circulating current called eddy current are induced in the iron core, and it says part of the input energy is lost as heat generated by these eddy currents. So while we try to stop the eddy current, yes, I spoke about how we could stop it, right? And we're going to look at that next, how we can reduce it. But it still happens, it still happens, and if you don't rectify it properly, then you will lose a lot of power. Well, not a lot, but small amount of your input energy, which is what you don't want, right? Because if you're losing your input energy initially, then at the end of the day, you would not be creating enough magnetic field to induce in the secondary coil. How can we reduce the power loss? It says by laminating the transformer core to reduce eddy current. That's one way. It says now, instead of a solid piece of iron, right, the core is made up of a very thin iron sheet insulated for each other by varnish, right? So in a sense, by rubbing a little bit of oil in between those sheets, it could prevent the flow of electrons, because as you can imagine, those varnish would be non-conducting. So hence why we would laminate the core, right? And it says winding the wires, right, or winding the core rather with low resistant copper wires, right? And it says using the thickness or the thickest wire, and what less number of turns that is practical, right? So essentially they're saying that another way how we could reduce power loss, right, is by way of using a very low resistant wire. So the less resistance you have, it's the more easier current is able to flow. The higher the resistance, it's the much harder current is able to flow. And with that now it's going to create a lot of heat. So if you reduce the resistance, which is the opposition to the flow of charge, then it means that you will literally be reducing heat and so forth. And another simple way is to just use a soft magnetic material inside of the core that would also reduce power loss as well. All right. So those are some ways that you should remember and know how to reduce it. Now we're going to take on a quick question here. Now the question is that a transformer is to be used, right, with an alternating supply of 240 volts to power a lamp rated at 12 volts and 3 amps. It says that the secondary coil of the transformer has 80 turns. It says assume that the transformer is ideal, right? It says calculate from the primary the number of turns and to the current. This is a very lovely question, right? First, they told us what our initial alternating current supply is, which is our alternating supply has this amount of voltage, right? Now, this is the amount of voltage that is required to turn on the lamp. So in your home, when you are plugging in a lamp in your home, right, to turn on some light, let's just draw a quick transformer here, because I want you to see that this is going to be a step-down transformer. Now, as you can see, the voltage that is required at the secondary is 12 volts. So it means that you're going to have less number of turns on the secondary, right? So this is the secondary. You're going to have less number of turns, but on the primary now, you're going to have a lot more number of turns, right? And of course, the power source, as we said a while ago, is 240 volts. That's your alternating source. So you always need to draw this diagram as well, in terms of your schematic. This is your primary. And then now we want to find out the number of turns on the primary, right? So all we will do is to use our equation. It told us already that's an ideal transformer, right? So we know several things. We know that the transformer, we know that so this is the lamp that you want to turn on. By the way, this is the symbol for a light bulb. So just be mindful that this is the symbol for a light bulb. So it told us that the lamp has a rating of 12 volts. So it means that I need a 12 volts on this end of my transformer, right? They told us the number of turns on the secondary. So this is going to be NS. So by way of just using our equation here, right? I know that VS is 12 because that's the amount that I need to power up the light bulb, right? I know that VP is 240 because it told me that already, that this is the power supply that is connected to the transformer. And then my number of turns on my secondary is 80. I want to find NP. So all I just need to do now is to transpose to make NP become the subject. So when I bring this across, it now tells me that NP is equal to 80 times 240 divided by 12. By the way of this, we can tell that the number of turns should be higher than the number of turns on the primary should be higher than the number of turns on the secondary. So 80 multiplied by 240, right, divided by 12, we're getting that NP is equal to 1,600 number of turns. So that's one part of the question, right? Then another part of the question now asks us to essentially find out the current. There are two ways we could have done this, right? We could have said, all right, since that it's an ideal transformer, power in is equal to power or we could say output power, right? So power in is VP times IP, which is equal to VS times IS. Now you might be IS. You might be wondering what is IS. IS is this amount because that is the amount of current that also needs to be passing through the wires so that this light bulb can actually work and all of that. So by way of just transposition, right? We want to find IP. So in essence, IP is going to equal to Vs times Is divided by Vp. So we could put in the values 12 times 3 divided by 240, right? So we're seeing that IP is equal to 0.15 amps. So that's our current. And that is expected. That is also expected in terms of the current. That current should be lower than what is at the output. So, right, that's pretty much what we need to do here. So you can take this one for yourself. Take this one for yourself, answer it, and then you can comment below, right, with the answers for what you're getting in terms of the number of turns on the secondary, and it says the current that is also going to be in the primary, right? So that's it. That's it for this particular lesson.